Welcome to lecture number 10 for ECE 461 Control Systems, LaPlace Transform Review. Now for the rest of the semester we're going to be switching gears. The first part of the class was on programmable logic controllers. That's one way to control a system. If you have something like a car wash, I've got valves I want to turn on, pumps I want to turn on and off. That's oftentimes done with the programmable logic controller. That's a graphical way to do timing, on-off controls, counters. Very common in industry. Another type of control system is controlling dynamic systems. That'd be like the speed of your car. When at the accelerator, it takes time for the car to speed up. The temperature in a room, if I want to do a reflow oven, I want the temperature to go up, maintain a constant temperature, then drop down. How do you control dynamic systems like that? That's what the rest of the course is looking at. And the heart of it is LaPlace transforms. That's the reason that signals and systems is a prerequisite for this course. You really need to have LaPlace transforms to do the rest of control systems. This class is a review of LaPlace transforms, basically what you need out of signals to get through this class. Now to start out, LaPlace transforms assumes all functions are in the form of e to the st. What that does is when I take the derivative of y, I get s e to the st, or s times y. So what this assumption does is it turns differential equations into algebraic equations in S. And the assumption is that algebra is easier than calculus. For example, suppose I have the following differential equation relating x and y. If I assume everything's in the form of e to the st, then s means derivative. So the third derivative of y becomes s cubed y. The second derivative becomes s squared, first derivative s, and so on. I can now factor out the y's and x's and solve. I get y is a function of x. This right here is called the gain, or the transfer function from x to y. S means derivative, so if I see a third order transfer function, that means this satisfies a third order differential equation. And essentially that's the gain. This is true for all s. For a specific s, like if I have a sine wave, I could plug it in and find the output. But really this means differential equation. And it goes both ways. If I have a transfer function, what that means is this is a differential equation. To find it, cross multiply. Note that sy means derivative of y, so s cubed is third derivative, s squared second derivative, s is first derivative, and so on. So this is the differential equation that corresponds to that transfer function. And also note, s means derivative. If I have s squared, that's the second derivative. The powers of s have to be integers. If it's s to the 2.3, what that means is I want the 2.3th derivative, and I have no idea what a 0.3 derivative is. So these have to be integers. Given a transfer function, there's a couple ways to solve for the output. It depends upon what the input is. This is true for all s. If I have a specific input, like x of t is 3 cosine 4t, then I can solve. This actually is not a differential or calculus problem. This is a phasor problem. In phasors, since this is true for all time, the output is also a sine wave. The frequency will also be 4 radians per second. What I need to know is how much is cosine, how much is sine. So what I do with phasors is take the input, represent it in phasor form. The real part is cosine minus j is sine. The frequency, everything's e to the st, e to the j4t is a cosine, so s is j4. So here's the gain everywhere. All I care about is what's the gain at s equals j4 times the input gives you a complex number. And what that number means is the real part is cosine minus j is sine. So here, this is really just an algebra problem using complex numbers. And also note, this is a filter. If I change the input, I change the gain. So if the input becomes 5 sine of 20t, do the same as before. Now the input is 0 minus j5, 0 cosine, 5 sine. The frequency is j20. Find the gain at that frequency times the input at that frequency gives you a complex number. And the output is just the complex number. Real part meaning cosine, minus j meaning sine. There's also superposition. If I have two inputs, treat that as two separate problems. The first input produces the first output. The second input produces the second output. Add the two inputs together, you get the total input. Add the two outputs together, you get the total output. That's superposition. That's what you covered back in circuits 1, circuits 2. In signals, you cover Laplace transforms. Now there's tables upon tables upon tables, Laplace transforms. I found you really only need 4. The Laplace transform of a delta function is 1. We'll just take that as an assumption, go back to signals to see that derivation. From that, the integral of a delta is a step. S means derivative. The antiderivative is 1 over s. So the Laplace transform of a step is 1 over s. Decaying exponential is a over s plus b. The pole, the root to the denominator is at minus b. That's that exponent. Again, this one we'll just assume. Go back to signals to see the derivation. And if I have b as a complex number, using Euler's identity, I can take these two, add them together, and get a cosine. And it turns out that twice the amplitude, 2 times a is the amplitude. The real part is your exponential. Complex part of the pole is the frequency of the sine wave. And it turns out the angle over the minus jc is the phase shift. You got a 50-50 shot. It's actually going to be this one. Again, if you want to see the derivation of that, please see the lecture notes on signals and systems. I think we do that in circuits 2, or circuits 1 as well. But usually just kind of take it as an assumption. Here's the table. From this, I can find the Laplace transform, or inverse Laplace transform of just about anything. For example, suppose I want to find the impulse response of this system. And impulse is defined as a delta function. The nice thing about an impulse response is the Laplace transform of a delta is 1. So take the transfer function, multiply by 1. That's Laplace transform of y. Now take the inverse Laplace transform, and that's an entry in the table. Second problem. Find the step response of g of s. Step is u of t. Laplace transform of a step is 1 over s. So this is going to be your gain times the input is the output. This one's not in the table, so what I need to do is partial fraction expansion. And here the idea is, take this guy, I can rewrite it as 2 separate terms added together. To find each of those terms, I use the cover-up method. Equals is a powerful symbol. That means these two are identical. When s goes to 0, this term blows up, goes to infinity, and that term doesn't matter. As s goes to 0, this blows up. The amplitude has to match. So if I cover up the s, a is equal to 5 over s plus 3, near s equals 0. And I get 5/3. b, when s goes to minus 3, this term blows up. So b has to be 5 over s as s goes to minus 3. So you just cover up the term you're expanding over, evaluate at that point, and you get your constants. So y of s is also equal to 5/3 over s minus 5/3 over s plus 3. This is in my table. This becomes 5/3 times 1 minus 5/3 e to the minus 3t per time positive. If you have repeated roots, there are tables for repeated roots. If you have 1 root, 2 roots, 3 roots, and roots. Another way to solve this problem is change the problem. That's actually a very common engineering solution. If I have a problem that's hard to solve, change the problem, but change it to one that's easy to solve and keep the flavor of the original problem. So here I have 2 poles at minus 1. I'm going to change it so one pole's at minus 0.99, the other one's at minus 1.01. You're going to have a very hard time telling the difference between these 2 step responses, but the one on the right doesn't have repeated poles, so I can just use the previous method. If I want to solve for complex roots, if you don't mind complex numbers, this is the approach that I prefer. The table entry I'm using is that if I have complex roots, do your partial fraction expansion, I'm going to have a complex term. The numerator will be a complex number. The inverse Laplace transform will be twice the amplitude, e to the minus bt, the real part of the pole, cosine of ct, the complex part of the pole, and the phase shift is the term over the minus j term. So for example, find the step response of this system. The approach is the input is a step, 1 over s. now do partial fraction expansion, I'm going to get 3 terms. The way you do it, the constant term, a, is cover up the s term, plug in s equals 0, and you get a number. Define b, cover up the s plus 1 plus j3, evaluate at s equals minus 1 minus j3, and you get a complex number. C will just be the complex conjugate of b, or you can calculate it. So the partial fraction expansion is 3 terms. 2 of them are complex. If you don't mind complex numbers, that's not a big deal. What this means, though, is the 1.5 is a constant. Double this term, 1.58, e to the minus t, cosine 3t, plus 161 degrees. It's this term, the 1 over the minus j. It's kind of a sidelight. In this class, you need a calculator that can do complex numbers. If you don't have one, make sure you get one. In the handouts, there's a video that goes along with how to do this using an HP calculator. I definitely recommend getting an HP calculator. HP 35s are about $40 on Amazon. They make your life a whole lot easier in this class. Now, comparing control systems and signals and systems, control systems is actually a lot easier. In this class, the x-axis is time. Time is a one-dimensional unidirectional vector. That means we're only using single-sided one-dimensional Laplace transforms. In signals, you can actually have non-causal systems. Think about an image. If I take the Laplace transform to the right, that's forward in time, to the left is backwards. So that gives you a two-sided Laplace transforms. Plus, for an image, I have xy, or x-axis, and y-axis. Gives you a two-dimensional Laplace transform when you have images. When you get to holograms in 3 dimensions, you have 3-dimensional non-causal Laplace transforms. We don't do that in this class. Again, we just deal with time. In addition, in this class, if you have a complex number, you have to have its complex conjugate. In signals, you don't have to have that. For example, with single sideband radio transmission, if I broadcast a signal, I've got the upper sideband and lower sideband. That's the complex conjugates of a complex number. If I get rid of the lower sideband, I can transmit the same information with half the energy. That's where you get single sideband transmission. That's where you get complex numbers without their complex conjugate. The math is kind of ugly, but if you can figure it out, you can cut the power consumption of radio stations by half. That's in signals and systems and communications. We don't do that in this class. This class, if you have a complex number, you have to have its complex conjugate. That's because we're dealing with real numbers, real resistance, real capacitance, real inductance. That makes life actually a lot easier. And fortunately, there's a program called Matlab. Matlab is actually written specifically for control systems, specifically for this class. It was designed to make binding step responses, impulse responses way, way, way easier. To do that, you first have to be able to input a system into Matlab. That's the command TF, that's transfer function. The first term is the numerator polynomial. That represents the numerator in decreasing powers of s. So 2, 3, 4 means 2s squared plus 3s plus 4. And the denominator polynomial. You can also input a system in terms of poles and zeros. The first one are the poles. This has a pole at -1. Actually, first one's the zeros. The first one has a 0 at -1 and -2. I've got poles at -3, -4, -5. And a gain up on top times 10. A third way to input is state space. In matrix form, I can have your x dot equals ax plus bu, y equals cx. We'll be doing that in a couple lectures. That's the third way to input the system. Once you get the system in Matlab, I can find the impulse response or step response really easily. Just to input the time vector, find the impulse response, find g of s, evaluate it at these time points, and plot it. Or the step response. You can also combine systems in Matlab. For example, if I input a system A, input a system B, if I want to combine them, say what is A times B, cascading them, that's just A times B. If I want to put them in parallel, that's just A plus B. And to illustrate that, for example, suppose I have the system A is transfer function of 1, 2, 3, denominator 4, 5, 6, 7. and it runs slow when you're streaming. Okay, there's your system. Want to find the step response. Let's go from 0 to 10 seconds, steps at 0.01. Y is the step response of A, T. Then if I plot the step response, there it is. Way, way, way easier than doing inverse Laplace transforms. You can also combine systems. Let's input in zeros, poles, k. I've got a 0 at -1, -2, poles at -3, -4, -5, and again up on top of 10. I can say now that C is A plus B. It'll calculate it and give you that system. This is where there's a kind of what I call a bug in Matlab. I've got pole zero cancellation. Min-real gets rid of the repeated poles. Once I have this system, I can now find the step response of C. And there's your step response. Again, way, way, way easier than you can do it by hand. Matlab is a real lifesaver for control systems. It's a program we're going to be using over and over in this class. So that's lecture number 10 for ECE 461 Control Systems, Laplace Transform.